So, good afternoon, everyone. My name is Svetlana Malinovskaya. I'm from physics department. So I'm, very grateful that I'm invited to be part of this forum. Thank you very much. And today we'll be talking about the topic on quantum enhanced detection and imaging using modern laser technology. So laser technology continues to advance and becomes more and more precise. And there must be corresponding progress in the techniques for imaging and detection and evaluation in general. These techniques might be at time, they must operate in time and be with high precision in both in time and frequency. Obtained data can offer new insights into this mysterious world of light-matter interactions and offer new prospects for abundant applications in various fields. So my group works on the development of quantum control methods, providing ultra-fast time and frequency diagnostics and molecular-specific imaging. We make use of the pulses that are called nowadays structured light altogether. These are laser pulses or laser radiation in general that is shaped for purpose, we may say so. Okay, next slide. It does not want to change. Okay, what altogether structured light is? It may be referred as to tailoring or shaping of laser radiation in all degrees of freedom. This is in time domain or in frequency domain to produce shaped ultra-fast time pulses. Alternatively, shaping can occur in the spatial degrees of freedom. This would be the polarization and also intensity and phase of the fields. For example, on this figure, this is the structured light donut type of shaping of spatial degrees of freedom. And this is, it is with the the arrows may show different polarization structures within this spatially modulated light. So the wavefront is not plane anymore. It may be helical or any kind of distortions associated with the wavefront propagation in space. All right. Okay, I found the way how it works. So effective solutions to create structured light are conventional liquid crystal pulse shaper on the left side. And also nowadays, this structured light may be created by placing optical elements inside of the cavity of laser. Then all kind of spatial shaping can occur, and this is the helical. This example on the right side is will produce the helical twist of light radiating from the laser. In my lab, we are working presently with the time and frequency shaping with pulses and produce ultra-fast shaped time pulses. A lot of work is done with linear chirp pulses. Also, we make use of sinusoidally modulated pulses and consider odd and even parity of such chirps. And we pay specific attention to phase log pulse trains. So huge sequences of pulses with the phase, relative phase fixed or predetermined from one pulse to another. They form pulse train, which when you take Fourier in frequency domain produces so-called optical frequency comb. This is the lower panel. The upper is the pulse train with specific properties of the phase, and the lower panel shows the Fourier transform of this pulse train, which is essentially a large dramatical number of very accurately positioned peak intensities, narrow band peak intensities. So this, which are called optical frequency comb. So it is unique. Well, it is as if about 1 million continuous wave lasers are shining simultaneously. You may imagine that. So this is unique spectroscopic tool. And well, there was Nobel Prize awarded for high precision spectroscopy using optical frequency comb, I think in 2005. So we also pay a lot of attention to using this unique tool for control. Well, the cornerstone method is stimulated Raman spectroscopy. That's what we are working with. Particularly, we look into the stimulated coherent anti-Stokes Raman scattering, known as CARS, which is 4-wave mixing process. The key innovation is in inclusion of quantum effects in the process and its optimization, which leads to qualitatively new results, new outcomes. The principal quantum property or quantity which provides or which is responsible for the intensity of the scattered light from a sample is coherence, quantum coherence induced by the incident light in, in a sample. It could be molecule, atom, any kind of matter, or where there are Raman active degrees of freedom. So, and thus, working with coherence, with quantum coherence and optimizing it is the route how we can enhance the signal, Raman signal, and to bring the imaging to qualitatively new level. So we have done, a lot of theory, semi-classical theory and pure quantum theory, which describes the interaction of radiation with quantum emitters, and particularly for CARS, coherent anti-Stokes Raman scattering case. For this scheme, we developed the solution which analytically maximizes coherence, vibrational coherence in within this sample. And on the right side, these are Wigner plots of the structure of the incident pump, Stokes and probe pulses that provide this solution, maximizing coherence, resulting in the optimal signal from the sample. I'll speak about it probably more if I have time in the connection for the remote detection. So altogether, this methodology has a number of advantages, and one of the prime of them is that the intensity is increased by 3 to 6 orders of magnitude compared to the case when we don't shape pulses, and significantly more, maybe by 10 orders of magnitude if we look into spontaneous Raman process. So we also obtained a patent which discloses a novel and innovative technique for molecule-specific imaging. It may be very useful for variety of diagnostics in medicine, like distinguishing between related species or distinguishing between cancerous and healthy cells, for example. So recently, do I have some time?
Okay, 1 minute.
Okay, so then these are a few technical slides that show application of the concept of maximizing coherence, particularly using CARS for remote detection, which is extremely challenging project, because the goal here is to be able to get a signal from a trace amount of molecules distant like 1 kilometer away from the receiver. So, and the whole idea is here on the creation of substantial coherence or good enough coherence that would preserve well, propagation of the signal back towards the receiver through large distances, because coherence would be, well, longer time living compared to all spontaneous effects happening in the air. And this could be done using shaping of the pulses, well, which would maximize vibrational coherence, as I showed in full level picture previously. So there is some technical slide. Bottom line on the this fourth anti-stocks components, this anti-stocks, my student S forgot some S here. So it demonstrates that the pulse has been anti-stocks component of the field, which is propagating in the backward direction, is being enhanced from one scattering event to the next one. I only may add one more important thing. That's what Jabir is working on right now. He's extremely talented student. So he implies machine learning model to analyze the phase of the propagating field upon each scattering event phase shifts, and it is numerical solution. The only way we find possible is to use machine learning algorithm to extract the phase to, well, to put it in the next propagating cycle adequately. So this is very tiny, delicate, but very important detail in our calculations. And that's pretty much all what I wanted to tell, because, well, on more general, well, note, in summary, I may say that we have very powerful machinery that provides with the analytical and numerical solutions how to maximize quantum properties in quantum emitters interacting with the classical electromagnetic field. And there is, well, many applications. Well, this method generally is widely used. It has been implemented in biomedical imaging methodology altogether for remote detection, for the deterministic excitation of single reader atom at ultra cold temperatures. So, and well, the only one outlook, well, detail I may say, I would like to focus now on the spatial degrees of freedom, and well, I see a lot of positive outcomes coming from this direction. Thank you.